document indexing in Lucene. You can see the document indexing here. In document indexing, the document in its raw form is extracted from a data adapter. This can be making an web API to retrieve some text output, or crawl a web page, or receiving an HTTP document upload. This can be done in a batch or online manner. When the index processing starts, it presses each raw document and analyzes its content. Typical steps include tokenize the document, break down into words, lowercase each word to make it non-case sensitive, but need to be careful with names and abbreviations. Remove stop words, take out high frequency words like the, but need to careful with phrases. Stemming, normalize different form of same word. For example, reduce run, running, ran into run. Synonym handling, this can be done in two ways. Either expand the term to include synonyms, that is, if the term is huge, add gigantic and big, or reduce the term to a normalized synonym, that is, if the term is gigantic or huge, changing it to big. At this point, the document is composed with multiple terms. Document equals term 1, term 2, etc. Optionally, the terms can be further combined into n-grams. After that, we count the term frequency with this document. For example, in a bigram expansion, the document will become document 1, doc1 implies term 1 colon 5, term 2 colon 8, term 3 colon 4, term 1 underscore 2 colon 3, term 2 underscore 3 colon 1. We may compute a static score based on some measure of the quality of the document. After that, we insert the document into posting list. If it exists, otherwise create a new posting list for each terms of n-grams. This will create an inverted list structure. There is a boost factor that can be set to the document or field. The boosting factor effectively multiply the term frequency, which effectively affecting the importance of the document or field. Document can be added to the index in one of the following ways: inserted, modified, and deleted. Typically, the document will first added to the memory buffer, which is organized as an inverted index in RAM. When this is a document insertion, it goes through the normal indexing process to analyze the document and build an inverted index list in RAM. When this is a document deletion, the client request only contains the doc ID. It reflects the forward index to extract the document content, then goes through the normal indexing process to analyze the document, build the inverted list. But in this case, the doc object in the inverted list labeled as deleted. When this is a document update, the client request contain the modified document. It is handled as a deletion followed by an insertion, which means the system first fetch the old document from the forward index to build an inverted list with nodes marked deleted, and then build the new inverted list from the modified document. For example, if doc1 equal AB is update to AC, then the posting list will be A colon doc1 deleted implies doc1, B colon doc1 deleted, C colon doc1. After collapsing A, the posting list will be A colon doc1, comma B colon doc1 deleted, comma C colon doc1. As more and more documents are inserted into the memory buffer, it will become full and will be flushed to a segment file on the disk. In the background, when M segments have been accumulated, Lucene merges them into bigger segment files. Notice that the size of the segment files at each level is exponentially increased. M to the power 2, M to the power 3. This maintains the number of segment files that need to be searched per query to be at the big O log n complexity, where n is the number of documents in the index. Lucene also provides explicit optimize call that merges all segment files into one. Here let's details a bit on the merging process. Since the posting list is already vertically ordered by terms, and horizontally ordered by doc ID, merging two segment files S1 and S2 is basically as follows. Walk through the list of both S1 and S2 together in the walk the posting list from both S1 and S2 together in shorter term order. For those non-common terms that appeared in one of S1 or S2 but not both, write out the posting list to a new segment S3. Until we find a common term T, we merge the corresponding posting list from these two segments. Since both lists are sorted by doc ID, we just walk through both posting lists to write out the doc object to a new posting list. When both posting lists have same doc, which is the case when the document is updated or deleted, we pick the latest doc based on the time order. Finally, doc frequency of each posting list of the corresponding term will be computed. Here you can see merge factor equal M and can explicitly call index writer dot optimize to merge all segment into one single document. Here you can see doc1, doc2, doc3 is connected to memory buffer posting list. After M documents are added, write out the posting list to the index segment here, level 1, and clear the memory buffer. Here the memory buffer is connected to index segment, here level 1, and index segments of level 1 are connected to index segments of level 2. If there is already M segments at level 1, step 1, merge M segments level 1 to a new segment of level 2 and clear the M segments of level 1. And here you can see whole the index of M documents here and whole the index of M to the power 2 documents here, and index segments of level 2 are connected to index segments of level 3 here, and here holds the index of M to the power 3 documents here. Now this is the end of my presentation. Thank you very much for watching it.